2.2, we're going to take limits as they approach positive and negative infinity. For problem number 21, we are asked to take the limit of a function as x approaches infinity, and the function is 2 minus x over x minus 1 times the quantity x squared over 5 minus x. And so, or x squared. And so basically what we're looking at is the end behavior. It's very simple. We could just graph this and look and see what the value is as we approach infinity. However, sometimes it's helpful to look at this and try to do this analytically. Some of the issues that we run into is that if we plug infinity in the denominators of those particular functions, they will approach 0. I already know the answer, but it's kind of easy. One approach we might take is to combine all the terms in the parentheses. So I find a common denominator, multiply the top and bottom by that common denominator to smash those two terms together. In other words, I'm going to set 2 equal to 2 over 1, have a common denominator. Now I have two fractions that I can multiply straight across. In the top, I end up with 2x minus 2 minus x, and then I just kind of push things through. What I'm looking at, though, is as I look at this function, and I will simplify the function in blue, I'm looking at the leading coefficient. Okay, so 2x minus x is going to be x minus 2 over x minus 1 times x squared on the top over 5 plus x squared. But when I go to FOIL that out, I'm going to get an x squared times an x, so my leading coefficients are going to be 1x cubed over 1x cubed plus a bunch of other stuff. That's enough to determine that I have equal degrees of polynomials in the numerator and in the denominator with the leading coefficients of 1. So my end behavior as I approach infinity should be 1 over 1. In other words, my limit should equal 1. If we plug that into the calculator, we'll see that it equals 1. Another way to look at that, the challenge for that is if you look at the second expression in the original limit, I'm going to get some ridiculously large number on the top, but then if we use that leading coefficient approach, you're going to get the same result either way. The reason we don't really care about the x squareds, in other words, if I FOIL everything all the way through, those are insignificant. When you take infinity and cube it, it's going to be a bigger infinity than infinity squared. So any squared term, any x to the first power or constant are somewhat insignificant. Our ratio of the leading coefficients, 1 over 1, is basically where we're going to be at as far as the end behavior goes graphically. And that's pretty much it. That's how you would solve it analytically. And most of you, if you plugged it in your calculator, you could clearly see that approaches 1. But sometimes we like to do the analytical and the graph, and if the two match up, then we know we have the right answer. For problem number 23, it's easier than it looks. We're asked to take the limit as x approaches 0 of the following function. Cosine of 1 over x all over 1 plus 1 over x. Well, remember that if I take a piece of pizza and I slice it into infinitely many slices, I'm going to have basically a 0 size slice. In other words, it's going to get very small. So when I think of 1 over infinity, it's really equal to 0. So by plugging infinity into the existing function, I'm going to get cosine of 0 over 1 plus 0, which is 1 over 1, and again the end behavior would equal 1. So as we approach infinity, we're approaching 1. There's other ways to do it, but this is another example. Clearly, if you graph it, you'll get that, and then we have the analytical to back it up. For problem number 25, again, we're taking the limit as x approaches infinity. Same thing here. We have sine of x in the top, and then we have some x terms in the bottom. The bottom is going to blow up because infinity squared is infinity, and any number that we put over infinity should equal 0. Any constant number over infinity will equal 0. So then we got to think, what is sine of infinity? Well, sine has a range of -1 to 1. In other words, it's bounded from above and bounded from below. So the greatest value sine of x will have is 1. The least value sine of x would have would be -1. So we could think in terms of any number between -1 and 1 over infinity. That's what we're thinking. So if you think in terms of that, any constant over infinity equals 0, so the limit is equal to 0. Again, you can verify the results by graphing the function sine of x over 2x squared plus x, and then just kind of zooming out on the graph and going towards infinity in the x direction, and you'll see that it quickly approaches 0. But again, we want to look at the graph and do the analytical. If the two match up, we feel pretty confident with our answer. For problem number 17, similar type of thing, except we're using a function that we don't use every day. It's called the greatest integer function. So that one I'm just going to graph on the calculator first. And I don't know, that's so funny. So to graph that, if you click on second and then click on 0, which has catalog, you could just kind of scroll through all the different functions and programs of the calculator until we get int open parentheses. And then when we get to that, that's the greatest integer function. So I'm going to graph the greatest integer function of x all over x. Now the greatest integer function is just a step function that automatically goes to the greatest integer. So 1.1 would be rounded to positive 2, 1.2 would be rounded to positive 2, and all the way up to 2. So it's a very specific step function that gives us the greatest integer of x. Well, when I plug that in over a number, it's got a weird kind of graph thing going on. And what we're looking at is the limit of this function as it approaches 0. I believe in your textbook, though, it says as we approach from the positive side. So we're going to approach from the right-hand side. We're going to follow the curve heading towards 0 from the right-hand side and see what that limit is. So I graph it. I'm going to have to zoom in a little bit. So I click zoom. I'm going to zoom by the origin where x equals 0. And if I hit trace, it doesn't look like there's even a function there. So another approach that I might take is maybe look at the table of values. Okay. If I hit trace, though, when I move to the left and move to the right, I'm not really seeing anything. If I let the value for x equal 0, it's not defined at y because of the function itself, the way we've defined it. So what I want to do is, if I hit trace, I can get kind of close to it and see. But now when I look in the table, my interval for x is counting by 1. So I've got 1, 2, 3, and so forth. So I need to go into my calculator and adjust how my table's set up. So I'm going to plug in 0.001 so that it'll increment in the domain 0.001. So now when I come back, it's very clear to see as we approach 0 from the right-hand side, our y value is also approaching 0. Now that one's really kind of tough to do analytically. That one you can almost, you've got to do it, well, we're still doing it. We're doing it numerically. We're looking at the table of values to kind of prove that it's heading that way. If we approach from the left-hand side, it blows up. But this limit is only looking for the right-hand side. So if we come from the right-hand side, from the positive direction, and we approach x equals 0, then our y value also approaches 0. If we come from the left-hand side, it goes towards positive infinity. So that left-hand sided limit would be positive infinity, but since the left does not equal the right, it doesn't have a two-sided limit. But that's okay. The problem in the book only asks for the limit as we approach from the positive side, and that value is equal to 0.